So far we studied series and their convergence, and but without a direct test on the underlying sequence to see whether or not the uh, series was converging. Well, this is going to change. I will discuss the ratio test. We can just look at the sequence itself and decide if it has certain properties, whether the series built upon this sequence is converging or not. What I will show is the following. Suppose we have a sequence an from 1 to infinity, and suppose we look at the ratios, the following ratios. So we divide an plus 1 by an and take the absolute value. And if this fraction has a limit L, which is smaller than 1, then what we may conclude is that the series Sn, which is a series of partial sums, which is denoted the sum n is 1 to infinity of an, is absolutely convergent. Also, the second part consists of showing that when the limit of for n to infinity of the fractions an plus 1 divided by an equals L, which is larger than 1, or the sum of n to infinity an plus 1 divided by an is infinity, then we may conclude that this sum is divergent. Yeah, so this gives a clear answer, a clear test. It's called the ratio test. So we take a ratio of two consecutive terms and we do it for all n. And if it has a limit smaller than L, equal to L smaller than 1, then we have absolute convergence. If not, if it's larger than 1 or even infinity, then we can immediately tell that the series is divergent. Okay, let's discuss it directly. The direct implications for two two sequences. So suppose we take the sequence an is 1 over n factorial. Yeah, n factorial is 1 times 2 times 3, etc. till n times minus 1, n minus 1 times n. So if we divide the the n plus 1th term by the nth term, then what is remaining is that we take a limit for n to infinity of 1 over n plus 1. Yeah, and of course this limit is 0. So the L in the theorem above would be 0, and it's clearly smaller than 1. So on the basis of the theorem, we can tell that 1 over n factorial, the sum over 1 over n factorial from n ranging from 1 to infinity, is convergent. Also, now let's look at the reciprocal of this sequence. So instead of 1 over n factorial, we look at n factorial. Yeah, we already know that the series for this sequence cannot converge as the limit for an to infinity is infinite. Yeah, so we already know that this one should diverge, but let's apply the ratio test here. So if we just take the limit of the fraction of an plus 1 divided by an in absolute value, well, of course we have positive elements here, so the absolute values are not doing so much. Then we get the limit for n to infinity of this fraction is the limit for n to infinity of n plus 1, which is clearly infinite. So we conclude on the basis of the ratio test that this series is divergent. Okay, a proof of this theorem is as follows. First, we're going to show the first part. So suppose that we have a sequence such that the limit for n to infinity of the absolute value of an plus 1 divided by an equals L, and this L is smaller than 1, right? So this means that the limit is L, that on the long run, if we take n large enough, then an plus 1 divided by an are close to a value smaller than 1. In particular, this says that the ratios that we form like this stay away from 1. Yeah? Another way of putting it is that to formulate it as such, there should be an r smaller than 1 and an index capital N, such that when we take larger indices, an n larger than capital N, then this would apply that the sequence, the value of the absolute value of an plus 1 divided by an should stay away from 1 and should be smaller than r, smaller than 1. Yeah, so the ratio of the values stay away from 1. That's the basic idea. Okay, what we then do have is that if we now look at a capital N plus 1 divided by a capital N, this one is also smaller than r, right? So, and in particular, if we multiply on the left and the right hand side by an, then we see that the absolute value of an capital N plus 1 is smaller than r times the absolute value of a capital N. Well, the same reasoning we can continue. So if we now look at the ratio of the absolute value of the ratio of a n plus a capital N plus 2 divided by n plus 1, we see that the absolute value of a capital N plus 2 is smaller than a n plus 1 in absolute value times r. And a capital N plus 1 in absolute value is smaller than r times the absolute value of a capital N. So we see that we get an additional factor r times a capital N absolute, right? So this can be continued by looking at the ratio, the absolute value of the ratio a capital N plus 3 divided by a capital N plus 2, etc., etc., which gives that a capital N plus 3 is smaller than r to the power 3 times the absolute value of a capital N. We can continue the same kind of logic, so that for the absolute value of a capital N plus k, we get the following inequality. By repeated application of the same logic, we see that this one is smaller than r to the power k times the absolute value of a capital N, right? So if we now add up the an's on the left hand side, what we get is the sum of k is 1 to L, let's say, over a the index capital N plus k absolute, which is smaller than the factorials on the right hand side. So we get the absolute value of a capital N times the sum over k equals 1 to L of r to the power k. Yeah, but if we look at the right hand side, we see a fixed value, which is the absolute value of a capital N, times a sum, And if we now let L go to infinity, we see that this sum over here, the sum over here will have a limit, right? Since this is a geometric series with an r small in absolute value smaller than 1, right? So this one is convergent for L going to infinity. Yeah, that's our first conclusion. So now let's continue. What we've seen is that now we have the, for all L, that the partial sum starting with k equals 1 over the absolute value of a capital N plus k is smaller than this sum, where k is 1 to infinity, right? And we see that the right hand side, this sum exists by virtue of the fact that r is an absolute value smaller than 1. Okay, but now on the left hand side, we keep adding up absolute values of the sequence an, right? So this sum on the left hand side is monotonically increasing in L, right? And it's bounded from above by the sum over here, right? So it's bounded from above by the sum on the right hand side. So we have a monotonically increasing sequence which is bounded from above. So we know that by the monotonic convergence theorem that the sequence on the left is converging. Yeah, so k equals 1 to infinity, the sum over all the elements, absolute value a capital N plus k exists, right? Okay, but then we also could add the first capital N elements as well, right? So we can just add the absolute values of the first n elements, which is a finite number, and the sum will still exist, right? So we also have that the series of with absolute values of all members in the sequence an, this sum also exists, right? So this sum is also exists. So what we've shown is that basically the series where we take the sum over the an's is absolutely convergent. Yeah, so if we have an absolute convergent sequence, this also shows that the sequence itself is convergent. So that concludes the first part of the proof. For the second part, we may assume that the limit for n to infinity of the absolute value of the fraction of an plus 1 divided by an is larger than 1. Yeah, so either the limit was equal to L or infinity. This in particular implies that for n large enough, we would have an plus 1 divided by an absolute is larger than 1, right? So for n large enough, we would have that an plus 1, an absolute value, is larger than an, right? Okay, but then the logic is that that it's very easy to see that we cannot have the limit for n to infinity of an absolute equal to 0, right? So the limit cannot be equal to 0. Since for n large enough, we see that the sequence of absolute values of an forms a monotonically increasing sequence. And this cannot have a limit 0. So what we conclude is when the absolute values are not moving towards 0, then we also don't have that the limit of the an's are going to 0. Yeah, so but we note that we should have a limit of an going to 0, which is necessary for convergence of a series, right? So we immediately can tell that the series the sum of n equals 1 to infinity of a n is divergent. And this concludes the proof.